Hi, Robin here, going to look at thinking concurrently. This is from component 2 and this is for the OCR A-Level Computer Science. With thinking concurrently, what we're trying to do is find ways of making an algorithm more efficient. But what's essential with this is that we understand what's meant by concurrent processing. So we've got three main types of processing that we can expect to use within a computer. We've got sequential, parallel, or concurrent. So we'll just have a look at those first, and then we can think about how that's going to affect the way that we apply an algorithm. With sequential, this is our standard way of using a processor. So we've got an order of tasks coming in, they're dealt with one at a time. It's only if there's a branch or selection that we would then jump to somewhere else in the code. But again, it would then just reset up another simple order of which it would work through the task. In other words, this is our bog standard way you'd expect a processor to work. Our second one or method of this would be a parallel processing, and this is very much what a GPU uses to sort of process large amounts of data. In other words, we've got the same data coming in to separate processors. In other words, by having them running parallel, we can obviously do things twice as quickly. When we think about this is obviously much more sort of processing intensive. It's therefore quicker, but it does then create additional cost. So by having more components, we generate other things like greater energy usage, more heat, etc., and that we don't really necessarily want, and therefore we want to look for perhaps a compromise. And this is where concurrent processing kicks in. And concurrent processing is the ability to use just one processor rather than having to have multiple of them. Now, when you think about this, what we've then got is the ability to process data and activities and actions and tasks like parallel processing. So we've got separate streams of jobs coming into the processor. But then what we're doing is we're able to process them just using one, which then is obviously far cheaper from a hardware point of view, from a cost point of view, than having to have multiple processors. But I'm hoping you're asking yourself, well, how is that possible? You could only ever process one task at a time, one instruction at a time within a processor. If we think of each task as a separate process, we would call that a thread. The idea of a thread is that you separate out each action. So when we're thinking concurrently, we think about the actions we want to perform and we consider which of those actions have to happen separately, have to happen one after another, or actually need to happen at the same time. When they're happening at the same time, we then want to maximize our processor as much as we possibly can. Each of those separate actions we'll call a thread, and therefore we want to process potentially multiple threads at once. As you can see here with the drawing, we've got one processor, we've got 4 threads coming in, and then what the processor is actually going to do is it isn't going to process all 4 at the same time. Instead, it's going to process thread 1. It will allow what we call a time slice, so between 1 to 10 milliseconds. Then it's going to move on to thread 2. Again, give it a slice of time. Then it's going to go on to thread 3, and then thread 4, and then keep going back to thread 1, keep going, keep going, keep going. I can hear you sort of hopefully asking yourself, well, that's fine, but that's not doing it at the same time, is it? Surely there'll be a big delay between activities. Well, there shouldn't be, because if you remember, a processor can handle over 3 billion cycles per second. In other words, that is too fast for a human to even be aware of, to notice, to see. And therefore, by moving through each of these, though it may seem really slow to a processor, they may be carrying out like a really large number of steps and cycles within that particular thread. To us, it appears like it's happening at the same time. Concurrent processing obviously sounds really good so far. We've been able to perform the same ability as parallel processing, but without having to use loads of separate processors. We've just done that within one. However, there are some complications with this. It does create a lot more complexity. It also means that we have to really think about the problem, what can happen, when and how and what order, and therefore we can actually start to create problems in doing so if we're not careful. If concurrent processing is ill, it goes to the doctors. And as you can see, we've got our 3 statements here: deadlock, race condition and starvation. And they're issues that come from this. So a deadlock is where every process is waiting for another process to finish. And what I mean by that is that you're effectively got a point where you can't continue until something else has happened. That could be like an input from a user, or it could be a calculation, or it could be something along those lines. We can also have what's called a race condition. That's where two processes are trying to use the same storage location. That obviously causes issues. Or you can have starvation, where a process is denied the resources it needs. And all three of these problems can come as a result of this mixed usage of a processor. But really important that we consider these issues and think about, will they have some other impacts as a result of them? Obviously, if we're dealing in a safety environment, we can't afford to have delays or sort of processes stopping or not being run properly, or conflicts of data. That'd be really dangerous. So if this was something to do like a safety vehicle, like a self-driving car or an aeroplane, perhaps it was a nuclear plant or some medical equipment, we'd have to be really careful, and therefore we'd be much better to opt for a parallel processing situation instead. And therefore we're kind of factoring that in. We can use concurrent processing perhaps in safe environments where, say, if you're running an operating system just on a home computer, if there's a delay, it's only really a problem with like how the performance of the computer is, and kind of you might get a slight glitch or a delay of some form. Whereas if this is for something that's really important and therefore is going to be life and death, we can't afford that risk, and therefore it'd have to be a parallel instead. Something like a GPU obviously uses parallel processing because, again, it would affect the performance of the video, wouldn't it? Make that sort of unwatchable potentially. Okay, well, thank you for watching. Really appreciate it. Please do help me to help others, and like and subscribe this. And then if you do have any comments, please just let me know. Any questions at all. I really do want to help you out if I possibly can. Cheers. Thanks a lot.